Hello everyone, welcome to the video lecture on refrigeration cycle. I'm following the textbook of thermodynamics and engineering approach. So that textbook, the chapter number is 11. So today we are gonna talk about refrigeration cycle. Basic stuff, basic definition of refrigeration cycle and what are the key components of a refrigeration cycle. Okay, so let's go ahead and take a look. What are the things that we need to know to in this refrigeration cycle. So the first thing we would like to define is that refrigerator and heat pump. Okay, so the refrigerator, in a common sense, we can define that whatever creates the cooling effect, right? That's a refrigerator, and the heat pump, it's simply whatever its heat pump is also a device which creates the heating effect, right? So you can see in this diagram that the refrigerator and a heat pump, right? So the refrigerator here, it's creating the cooling effect within this closed chamber, and then the heat pump, it's creating the heating effect within this residential you know area. So basically a residential system, right? So you can see the difference between the heat pump and the refrigerator. Basically the refrigerator, it's also operating in between two thermal reservoir, right? One is that high temperature and another is the low temperature, and heat pump is also working in two thermal reservoir. One is high temperature, another is low temperature. However, you can see that the working principle of both of them are pretty similar. They are taking the heat, QL amount of heat, from the low temperature reservoir, right? And both are trying to deliver the heat, QH, to a high temperature reservoir, right? So however, one is creating the cooling effect, another is creating the heating effect. So that's the difference between refrigerator and heat pump. So if we define the refrigerator, what is the refrigerator? Refrigerator, excuse me. The refrigerator is nothing but a device that produces cooling effect by transferring heat from the region to high temp region. Right, so that's the it's a refrigerator is that's the definition of a refrigerator. Refrigerator is nothing but a device that produces the cooling effect, first of all, and then it works in between low temperature reservoir and high temperature reservoir, right? So it's basically extract heat from low temperature region to high temperature region to produce the cooling effect. So that's the definition of the refrigerator. Now we know the definition of the refrigerator, then what would be the definition of a heat pump? So the heat pump, it's basically a device that produces or creates the heating effect, right, by transferring heat from low temperature region to high temperature region. Okay, So, however, I mean they're the same. The only the difference is between the refrigerator and heat pump is the heating effect and the cooling effect, right? So it also it's a also device that produces the heating effect by operating in between two reservoir, which is low temperature reservoir and high temperature reservoir, or low temperature region, right, and high temperature region. So that's the definition of the refrigerator and heat pump. So let's take a look at how we can define the effectiveness or efficiency or performance of these devices. So in the previous cycle or previous chapters, when we discussed about thermodynamic cycle, for example gas power cycle or vapor power cycle, we talked about the efficiency. However, in the refrigeration cycle, we are no longer using the efficiency. We are using a new term which is called COP, right? COP instead of efficiency will be used. COP instead of efficiency. So what is the COP, right? COP, it's coefficient of performance. So basically we'll define the COP for both of the device, right? So for example, COP, coefficient of performance for coefficient of performance for refrigerator R equals to the desired output versus divided by required input, right? So what is the input of the refrigeration cycle or refrigeration system? So basically the input is equals to W net to operate this device, right? Basically right here. So that's the input of this cycle, and then output of this cycle, it's basically the QL, how much heat we can extract from this conditioned space or this closed space. So that's the output to create the cooling effect. So basically we can write this is the cooling effect. Desired output means that cooling effect, right? Divided by required input, which is nothing but the work input, right? So the cooling effect, we saw that would be QL, right? Cooling load divided by W net in. So that's the COP of refrigeration cycle. Okay, now COP of a refrigerator. Now let's take a look what is the COP of a heat pump, right? HP. So the COP of a heat pump is nothing but the heating effect divided by work input, right? So heating effect, if we express that one by QH divided by work input W net in, right? So that's the definition of COP of heat pump. So now we know the definition of the COP of the heat pump and refrigerator. We'll use them oftentimes to analyze the cycle. Okay, so now let's take a look to the definition. One more definition that is basically expressed to expressed to determine the cooling effect or the heating effect, which is called ton, right? So usually in commercial area, or basically when we buy a refrigerator, or even in air conditioning system, we oftentimes ask how much is the capacity of the refrigeration capacity or the cooling capacity, that is expressed by ton. So let me add one more page right here. Excuse me. Yeah. Okay, so basically the cooling capacity is expressed by ton, right? So what is the ton, right? What is the definition of the ton? Definition of the tone is basically the the capacity of a refrigeration system that can freeze 1 ton of liquid water at 0 degrees Celsius, okay, into ice at 0 degree Celsius in 24 hour thing. Actually it will be 24 hour is known as TOL. Okay, so the capacity of a refrigeration system that can freeze 1 ton of liquid water at 0 degrees Celsius into ice which is also at 0 degrees Celsius in 24 hours. Okay, so that's the definition of the ton. So now if we take a look at the ton, how much energy is required, right, to create that 1 ton of refrigeration effect, right? So basically 1 ton of cooling effect equals to 211 kilojoule per minute, right? Or if we express it in BTU, 200 BTU per minute, right? 1 ton. Okay, so now we know the definition of the ton, or definition of the cooling capacity of a refrigerator, right? So let's take a look one more thing about this heat pump and the refrigerator. So the relation, we defined the coefficient of performance for the heat pump and coefficient of performance for refrigerator. The relation between the relation between refrigerator, excuse me, this will be relation between refrigerator and heat pump COP is basically COP of heat pump equals to COP of refrigerator plus 1. So from this relationship we can see that if the heating QL is constant, QL and QH is constant for both of them, then like basically the QH, right, QH and QL is constant for both of them, then basically we can say that the COP of heat pump is greater than COP of refrigerator. Okay, so that's the relationship between the of the coefficient of performance between the refrigerator and heat pump. So now we know that three things. Number one is the definition of the refrigerator and heat pump. Number two, we know that how we can define the effectiveness of a refrigerator or a heat pump, which is the coefficient of performance. And number three, we know that how we can define the capacity, cooling capacity, right? And also as well as we know the relationship between the coefficient of performance of heat pump and refrigerator. Now let's take a look at a ideal cycle, right? Ideal refrigeration cycle. So ideal refrigeration cycle is basically based on the Carnot cycle, right? So the Carnot cycle is not an actual cycle, it's completely idealized cycle, and when the ideal cycle is proposed, it has some limitation, and then when people try to solve those limitations, they came up with the actual device, right? So in the reversed Carnot cycle, why we use this term reverse? The first thing is the about the Carnot cycle. Number one assumption, it's an ideal cycle, right? Ideal cycle, right? And number two, it's reversible. All the processes are reversible. There is no irreversibility in any of these devices, right? So all those devices are reversible. And then number three is basically it's assuming that since all these processes are reversible, then the cycle we can operate the cycle in a reversible manner or reversed manner. How? Reversed manner. How we can operate this reversed manner? We saw that in previous chapter when we talked about gas power cycle, or when we talked about the vapor power cycle, we saw that the heat rejection is happening in the condenser when it's coming out from the turbine. However, if we do, since all of these devices are reversible and they can operate in a reverse manner, then heat rejection is happening in condenser before entering to the turbine, right? And then heat addition is happening after the turbine. So that's the process which is reversed, and that's the cycle, Carnot cycle, known as the reversed Carnot cycle. So everything happening is in a reversible manner, right? Like this way. However, in previous chapter we saw that everything is happening in this direction, right? So that's the difference between this reversed Carnot cycle and simple Carnot cycle. So let's take a look what are the things or what are the assumptions they made to came up with this reversed Carnot cycle, right? So the assumptions. So the number one assumptions in this Carnot cycle is that you can see right here, this process 1 to 2, it's basically the heat addition. Process 1 to 2 is heat addition, right? And then process 2 to 3 process 2 to 3, it's basically isentropic compression, right? And then process 3 to 4 is heat rejection. Let me write it in this side. Process 3 to 4, it's constant pressure heat rejection. Heat rejection. Okay. And then process number 4 assumption, which is the turbine, right? Process 4 to 1, isentropic expansion. And this heat addition is also constant pressure. Okay, constant pressure heat addition. Okay, so those are the assumptions. So if we take a look what are the TS diagram of this ideals reversed Carnot cycle, then the TS diagram will look like this. So this is the saturated dome, and then basically you can see that the process 1 to 2, its heat addition is happening right here. So, and this process and 1 to 2, you can see it's completely in liquid phase, right? So then process 1 to 2, it will be basically right here, 1 to 2, this is the heat addition. Okay, and then from 2 to 3, it's basically this one, 2 to 3 right here, it's compression, right? Temperature and pressure is slightly increasing. And then 3 to 4, it's basically the condensation is happening, where the the Q out, it's happening, or heat rejection. And then 4 to 1 is that isentropic expansion in the turbine. So this is the compression, right? Compression, and this is the turbine or expansion. Now, what is the limitation of this ideal cycle? So the first limitation, you can see that the turbine is or the compressor is handling, compressor input is the liquid phase, right, which is not possible. So this thing, this liquid, you can see the liquid vapor mixture in 2 to 3 process. So number one limitation is that number one is that compressor input is liquid. Compressor input is liquid and vapor, right, which is not desirable at all, right? So I mean, compressor cannot handle liquid vapor or two-phase fluid. And then number two limitation of this cycle is that this basically that the turbine, it says that it's taking the gas and it expanding to the liquid. So turbine can also there is a limitation that when we put like liquid in the turbine blade, when we expand the gas and it becomes the liquid, and that liquid also deteriorates the turbine blade, right? So that's one type of limitation, turbine blade limitation, right? Now what else is its other limitation? So another limitation of this Carnot cycle is it's that when it operates in between, let's take a look here, when it's operating in between this evaporator and the condenser, they're saying that this evaporator or that heat addition in the evaporator, it's a constant or isothermal process. It's very difficult to maintain the isothermal process. As well as the condenser, they're also saying that it's isothermal process, right? So although number three, although it's possible to achieve achieve the isothermal, although it's possible to achieve the isothermal condition at 1 to 2 and 3 to 4. However, this it is quite impossible to operate the cycle with the liquid vapor at the compressor and the turbine. So that's the limitation of the Carnot cycle. Now we know the limitation, right? So we should come up with the idea, or we should come up with the solution that what are the things that we should take care about this ideal cycle and replace them, and basically develop a actual cycle. So we'll take a look on that actual cycle tomorrow class, or the next class, right, about what are the key components and how those limitation we can basically mitigate or avoid, right, or resolve, and then come up with the actual cycle that can be used in the refrigeration system. Okay, so thanks for watching this video. We'll come back with another lecture video.